Hi, everybody, and welcome to this episode of Crowded Beaker Solves. In this episode on Lewis structures, we're going to revisit Lewis structure setup that we already did in a previous video. So if you would like to see how these Lewis structures are drawn, you can go back to the previous video. I'll put a link in the description below. But this is the three resonance structures for thiocyanate ion. And in the previous video, we talked about, what would be the most likely scenario here? Do all of these exist equally as the bonds and the electrons resonate around the molecule, or is one more likely to occur, one more stable? And in order to answer that question, we can use a tool we chemists use called formal charge. Now, formal charge is the apparent charge on an atom in a molecule. And it's different from an oxidation state. An oxidation state is the charge that we would give it if the molecule broke apart and everybody took off with as many electrons as they possibly could. Some would have more, some would have less, and we would assign the charge that way. In this case, we're going to assign the charges based on how they're sharing the electrons in the bonds itself within this molecule. So it's slightly different than an oxidation state. And the way to do it, there is a formula for how to do it, and you might want to learn this formula, but it's the same formula every single time. If you wanted to assign the formal charges to atoms that are in a molecule, the way you do it is you start with the number of valence electrons the atom would begin with as you grab it off the periodic table to put it in a molecule like this. And then you're going to subtract the number of lone pair electrons that it has, plus 1/2 of the bonding electrons that it has. So this is you're adding these and then subtracting it from the original amount of valence electrons. We do the half of bonding electrons because these electrons are shared, and so we'll give one to each of the two atoms for each of the bonds that are actually there. So I want to demonstrate it real quick, and I'll let you pause the video and try the other ones from the resonance structures to see how you do. So the formal charge, I'm just picking the first resonance structure that we did. And for sulfur, for example, sulfur, according to the periodic table, will start with 6 valence electrons. That's what it starts with. Now, in the final molecule, it has 4 lone pairs of electrons, right there. And it's also got 2 bonds, which is 4 electrons, but half of those belong to the sulfur. So 2, actually, I'll do 1/2 of 4, so it's a little more clear where it comes from. And we get a formal charge of 0 because 6 minus 4 plus 2 is 0. So this formal charge is 0. So sulfur has no charge in this molecule. It's just hanging out with its 6 valence electrons. Carbon will start with 4 valence electrons. That's how it begins. And it's got 0 lone pairs and 1/2 of its 8 bonding electrons. It's got 4 bonds for a total of 8. And that will also work out to a formal charge of 0. And finally, let's do the nitrogen. Nitrogen starts with 5, and this nitrogen has 2 4 lone pair electrons, and also 2 bonds for a total of 4 electrons, so 1/2 of 4, and that gets to be a -1. So this nitrogen is a -1. One way to check that you're doing these appropriately is that the sum of the formal charges has to add up to the overall charge on your molecule. So 0 plus 0 plus -1 does give me the -1 overall that this ion would have. And so I can be reasonably sure that that is correct. So this is the formula. Take a moment and write it down. And then we'll go ahead and put the other ones up there. We'll go back to my original statement about drawing a Lewis structure for thiocyanate ion. So take a moment and pause the video and see if you can finish assigning oxidation states to the other 2 resonance structures. Actually, let's go here for thiocyanate ion. Okay, so if you finished assigning your formal charges, and if you got a formal charge such as these, we already did the 0, 0, -1 version. This one is -1, 0, and 0. The negative charge just gets swapped over to the sulfur because it has more electrons. And in the final one, we have +1, 0, and -2 as our formal charges there. So how does this help us to decide which one is actually best? Well, the kind of general guiding principle here is that the resonance structure that is most likely is the one who's kind of most relaxed at its lowest energy state and has the lowest set of formal charges that are there. These two both have -1 and a couple of zeros. This one has a +1 and a -2 and a 0. These are higher magnitude formal charges, and they are very much less likely to exist. So as far as picking which one it would be, I would probably cross this one out and say, no, it's probably not going to be that one because we have elevated charges within the molecule. Then the question becomes, and this is a little more advanced question, how do we decide which of these two is most likely? Are they equally likely to exist because they have the same set of formal charges? Um, they probably exist at some point or another, but I think that the better resonance structure to choose as the most favorable one is this one, because the negative charge, if you're ever trying to decide this, pick whichever one has the negative charge on the most electronegative atom in the molecule. And in this case, nitrogen is more electronegative than sulfur, and so it's probably more likely to be on that one. This one is probably okay too, but I think if I was picking, I would probably pick that one. Okay, so there you have it. A way of using formal charges to decide which molecule is the best in a series. And if you have any suggestions of anything you'd like me to draw or solve, please send them to me. In the meantime, happy drawing and have a great day.